Hey everyone, Mr. Shatter here to take a look at examining the derivative of exponential logarithmic functions. In this video we're going to consider the derivative of 4 different types of functions, and we'll learn 4 formulas as a result. Let's get started. The first formula we're going to consider is the derivative of an exponential e to the x power. Here's a brief proof of the derivative. So if you use the definition of the derivative in this first line right here, limit as h approaches 0 of e to the x plus h minus e to the x over h. And then in this step right here, we're just separating using power of exponents. And then we factor out an e to the x. And since e to the x has nothing to do with the variable h, because our respect here is h, you can actually just pull the e to the x right out and pull it out of your limit because it's not needed in there. It's a constant technically in regards to h. And that leaves this piece right here, which we can actually ask the graphing calculator for some help. So let's go and put this in the calculator. All right, scooch this off to the side and we'll turn on our calc. So what I've done is I put in my function into y equals, and then what we'll do is we'll consider its limit as you approach 0. So what I'm going to do is adjust my table to start at 0 and to go up by 0.001. And this will allow me to get a good glimpse of what's happening to the left and to the right of 0. And so I'm just going to look right here at negative 0.001. It's approaching 0.99995. And then as we approach 0.001, it looks like it's going to 1.0005. And so that's enough evidence to successfully conclude that the limit as h approaches 0 of this function is 1, just with the help of the calculator. And then therefore e to the x times 1 is just e to the x. So e to the x is a unique derivative. Its derivative is actually itself. Its derivative is actually itself. But you got to be careful. You have to chain the u, the power in this formula. So in general terms, the derivative of e to the u is equal to e to the u times the derivative of u with respect to x. So this is the chain rule, multiplying by the derivative of the exponent. Let's try an example. It says find the derivative of f of x equals 3e raised to the sine x power. So in this problem, the derivative f prime of x is simply going to be 3e to the sine x, which is the e to the u piece, times by the derivative of u, which in this case is sine x. This is our u. So the derivative of sine x is a cosine x, and that derivative doesn't really simplify at all. All right? Here's our next formula. Our next formula is the derivative of a to the x. And before we actually consider the proof of a to the x, let's rewrite a to the x power using an exponential. So let's rewrite it as e raised to the natural log of a to the x. Okay, now rules of exponents, or rules of logarithms rather, say that if I actually raise e to the ln, they're inverse operations, they cancel each other out, leaving me with an answer of a to the x. So these functions are in fact equivalent. So I'm going to use this one in the proof in the following page, okay? Here's the proof. So the derivative of a to the x is equal to the derivative of this function. This is from the previous page, okay? And this is actually equal to e to the u times the derivative of u. It's just an exponential. We just learned that derivative rule, right? So this is the u, and this is the u, so we're going to take the derivative of that right there. And that, as a result, is just equal to the natural log of a, because natural log of a is a constant. So this is like, what's the derivative of 3x if this is f of x? And then f prime of x is just equal to 3. It's the same thing with a natural log. Natural log a is a constant. So the answer and the formula that we're going to use is the derivative of a to the x is equal to a to the x ln a. But you must be careful, once again, with the chain rule. So here is the formula in terms of u. So the formula in terms of u is the derivative of a to the u is equal to a to the u times the natural log of a times du dx. Okay, so this exponent is a u, and this is an a. I know it's a little hard to read with that typeface, but that's a u and that's an a, and we're multiplying by du dx. Okay? And let's try this example right here. In this problem, it looks like the value of a is 2, and the value of x squared plus 2x, that's u. So the derivative formula tells us that the derivative of this function, f prime of x, is equal to a to the u, so that's just the original, multiplied by ln a, multiplied by the derivative of u with respect to x, which is 2x plus 2. So this product, which doesn't really clean up either, ln2 is a constant, 2x plus 2 is just this other function, and then our a to the x or a to the u power, nothing combines here. So this is what the derivative would look like. Okay, let's look at the derivative of the natural log of x. So in order to do the derivative of the natural log of x, we're just simply going to take y equals ln x, and we're going to change it to exponential form, which is e to the y equals x, something we learned back in pre-calc. And then we're going to take the derivative of both sides using implicit differentiation. And that yields e to the y dy dx, using the derivative right here of an exponential that we just learned in a couple slides ago. And the derivative of x is just 1, of course. And so if you rearrange terms, dy dx is equal to 1 over e to the y. But in this step right here, we said e to the y is equal to x. So I'm just going to make that substitution right here so that the derivative is equal to 1 over x. Just once again, be careful with the chain rule. So the derivative of the natural log of u is equal to 1 over u times du dx, making sure you chain that respective u there, okay? Got to make sure you multiply by the derivative of u. Let's try an example. In this case, the u is the sine 3x. This is our u. So f prime of x is equal to, and the formula says to do 1 over u, so we'll do 1 over u, so 1 over sine 3x, multiplied by the derivative of u, and the derivative of sine 3x is actually going to be a little bit of a chain rule. We're just going to take, first of all, the derivative of sine, and we're going to get cosine 3x. But then we have to multiply by the derivative of the 3x, because that's an additional chain rule, and that derivative is simply 3. So the formula for this one actually simplifies to 3 cosine 3x over sine 3x. And then cosine over sine, if you want to, you can simplify to cotangent of 3x. So this derivative would be 3 cotangent 3x, and that would be that. One last derivative formula, and that is the derivative of a log base a of x. So we're no longer taking the derivative of a natural log. In order to solve this derivative and look at its proof, we're going to rewrite log base a of x using the change of base formula. The change of base formula says you could pick a logarithm of any base, and it's just equal to that logarithm of that base of this number right here, the logorand, and then divided by the logarithm, that same base logarithm of the base of the original log. Okay, so in this example, we're going to choose to use base e, which is natural log, and that's what we're going to take the derivative of. Okay, we're going to take the derivative of the natural log of x over the natural log of a. And then in order to take the derivative of the quotient of natural log of x over natural log of a, you have to understand that we're taking the derivative with respect to x, right? So the natural log of a is actually just a constant. This isn't a quotient rule. This isn't a quotient rule. And so what you can do is you can actually just remove the natural log of a from the derivative altogether, because it's a constant, and then just take the natural log of ln x, which we just learned in the previous slides is 1 over x. And so therefore you get a formula of 1 over x ln a after everything is done and simplified. But once again, remember the chain rule. Let's look at the formula in terms of u. This one is the derivative of the log base a of u is equal to 1 over u ln a times du dx. In this example, f of x equals negative 3 log base 4 of 5x. And in this example, we have an a value of 4, and we have a u value of 5x. So if we use the formula, f prime of x equals, it's going to be 1 over u, which is 5x, times ln a, which is 4, times the derivative of u, which in this case is just 5. And so we can rewrite this if we'd like. We can simplify it to 5 over ln 4 times 5x. And the 5s would just simplify and give you 1 over natural log of 4 times x. Making sure to be careful writing the natural log of 4 times x like that, and not writing the natural log of 4x kind of looking like that. So you can, if you wanted to, even take the x and just put it in front of the natural log. That might be a little bit cleaner actually. And then, yeah, that is our, here, we'll just get rid of that. That is our derivative for that problem. All right. Let's look at an example using these properties, these newfound properties. But first, actually, before we move on, it looks like in the previous problem, looks like I dropped this -3 altogether, so we're just going to put that back in this problem. I'll just put it on top right here, and then we'll multiply by -3 right there, and this is just going to be, instead of the 5's right there, this will just be -3 over x ln 4. All right? Okay, let's take a look at this example number 5. So example number 5 says the spread of flu in a certain school is modeled by the equation P of t equals that, where P of t is the total number of students infected t days after the flu was first noticed. Many of them may already be well again at time t. So part A asks you to estimate the initial number of students infected with the flu. Well, in order to estimate this, all we really have to do is plug a 0 into the original formula. And before we do that, we could simplify this original formula as just simply being 100 times 1 plus e to the 3 minus t, all raised to the negative first power. So it may come in handy to do that. So all I have to do in this problem is plug a 0 into the value of t. So this is going to be 100 times 1 plus e to the third power, all raised to the negative first power, and then this is going to be equal to, I think, 5 students. 5 students. Okay, so just, you can use a calc for e to the third. You can use a calc for that. B. How fast is the flu spreading after 3 days? Well, in order to calculate rate of change, we know we need derivatives. So really your job is to plug a 3 into the derivative of the function. So let's calculate the derivative. So the function is p of t, so it's going to be dp over dt, which is the derivative of the function p with respect to time, is equal to the 100 times the -1. The -1 is going to come down, so that's going to be -100 times 1 plus e to the 3 minus t power, and that's going to be raised to the power of -2 now because we have to reduce by 1, and we need to multiply by the derivative of the inside. Well, the derivative of the inside is simply the derivative of 1, which is 0, plus the derivative of e to the 3 minus t. Now the derivative of an exponential is the exponential itself multiplied by the derivative of its exponent, which in this case would be a -1. Okay, so let's clean up our derivative. So our derivative is actually going to equal 100 e to the 3 minus t power, all divided by 1 plus e to the 3 minus t power, all raised to the power of 2. Okay, and all you have to do is plug in a 3 here. So we're going to plug in t equals 3, and again, you can use the calculator. That's going to come out to 25. And the rate of change here is actually going to be students. 25 students per day. Okay, so that is the answer to part B. This is the answer to part A. Okay, and again, this will be calc active, so you can plug that in calc. Part C, when will the flu spread be at its maximum rate, and what is that rate? Okay, well, in order to answer that question, first of all, you need to basically find the maximum of the derivative. So there's 2 ways to do that. You could either find the maximum of the derivative, so you could plug this into your calculator, this function right here, and you could find its maximum, or you could plug the derivative of this function in your calculator, and then you could find a 0 of the second derivative. Either way you do it, you should get a value of 3,25 as the maximum of the derivative, max of derivative, or it could be a 0 of the second derivative. Specifically, what these numbers represent is that it would be 3 days to reach a maximum, and it would be 25 students per day. That's when the rate of change is going to be the maximum, meaning when this flu is going to spread at its maximum rate. So 3 days in is when we're looking at a big rate of change of the flu spreading around the school. All right, so that is the problem.